Which of the following solutions has the highest fluorine concentration? This is a pretty typical multiple choice question. What you need to remember here, so this, for example, I'll do A and I think you'll get the idea. Calcium fluoride here is 0.05, but that's for the molecule. For the fluorine, there's 2 moles of fluorine for every 1 molecule, so it's double this is the fluorine concentration. For this one, it's just as is, because there's 1 fluorine per molecule. See how it works? Go through and multiply your get. Okay, next, yes?
Oh my God.
Can you pass me that? Number 8 on history, whatever the heck this is. Oh, okay. This would be a common, like, chapter 1, chapter 2 question. This is on page 130, number 8. Page 130 of the practice exam reader. Pass that back. It's this one. Let me just do it very quickly for you. Is that okay? Oh, where'd you go? Oh, there you are. Okay. I lost you. Okay. What you want to do, remember, and it's not uncommon to have a density question on the final. You know the density, it's 11.35. It gives you the number of atoms. You have atoms, you need to convert that to moles using Avogadro's number and then grams. Is that okay? And then the volume you pretty much have, that's what you want to find is volume. So you got the density, the mass, we need to know the volume, but they don't want to know oh, maybe it's even a little easier. They don't want to know they want to know the volume of a block that has this many atoms of lead to a 4, okay? And you have the relative abundance. So that means that, let's see, we've got the density, this density of lead. Okay, and then the atoms, 8.34 times 10 to the 21. But that's of only lead 204. You want the total number of atoms. So when you do this conversion, there's one more step. Okay. Let me ask a concept question. Is there very little of this compared to the total number of lead, or a lot? A little. How did you know that? That's right. Because the abundance is 1.48. So how do you get the total number if you know the percent abundance? Divide by? Yeah. Oh, it's really tiny. Is that better? Yeah. So you know this gets you the total number of lead. That's what's ultimately going to be the mass, and that'll get you to the volume. Is that okay? This is the key step right there. Okay, next. Yes?
Do you mind going back to the V-shaped Lewis structure again?
Yeah, just a second.
On the question, I noticed it said 95-degree angle. I don't know how...
Good question. Yeah. How did they get 95?
Yeah.
Okay. So let me ask you, ignore the brown part here. That's a single bond. Okay. What's the ideal bond angle, anybody? 109.5 because there's 4 groups. That's the ideal bond angle. That's all you're expected to know. They just for fun told you the 95. That's the actual bond angle. There's no way you would ever know that, and there's nothing you do with that number. Okay? So the only thing that you have to know is that ideal bond angle. Okay? Way in the back, yes, with the white shirt.
Which has a greater bond length, NO plus or N2 plus?
What has a what bond length?
Greater bond length. NO plus or N2 plus?
What was the second one?
N2 plus.
Okay, how do you solve this? Okay. That's funny. Which has a shorter bond length? Shorter bond length. Okay, probably what I would do, let me give you the method and see if this works for your brain, and then we probably won't do it. Okay, but this is not an unusual question. You would draw the MO diagram for N2 plus and find the bond order. Okay? Does that sound reasonable? Should do that? If not, I can do it. Okay, you seem okay. You would do the same for this and find the bond order. Okay. A greater bond order means what about the length? Longer or shorter? There we go. Is that cool? Yeah, that's how you do it. So that's why I'm saying, if you're okay, I'm just not going to draw the MO. Okay. Yeah.
Page 109, number 23.
Page 109. Just a minute. This one. Page 109, number 23. Okay, first, let me explain the question. After I explain the question, let me see what part got you stuck, okay? So the question is, I need to go from 50% by mass of H2O2 to 3%. I'm ending with 20 gallons. I want to know how many gallons I have to start with. And I have the density of each solution. What kind of problem is this? Yeah, it's dilution, because I know that the concentration is changing, and I know that the volume is changing. So I'm using the following formula. And this is 20 gallons here, and this is question mark, okay? Normally, this would be easy right now. You just put in the molarities. You don't have the molarities. If these densities were the same, you could put the percent mass straight in. Because the density changes, the molarity is changing in an unexpected way. So that means you need to convert to molarity on both sides, 50% and 3%, and plug it into the question. You don't need to change the gallons because you're getting gallons as an answer. You got that? Okay. There's the dilution part of the problem, and then there's a conversion to molarity. Are either of those more confusing to you, or you're totally okay? Okay, there we go. Okay. Not everybody is okay. So you go 50. The 50% changes to this. To change it to a fractions is 50 grams over 100 grams. This is grams of H2O2 on the top and grams of solution on the bottom. This is the same as writing 50%. Then you need to convert to molarity. That means the top is moles, the bottom is volume. So let's do the bottom first. Change grams to volume. You're going to use the density to do that. So 1 point, this is a solution density. And notice what happens. I'll use a different color at the same time. The grams cancel. I'm left with milliliters. Am I okay for molarity yet? Not quite. I need liters, not milliliters. So 1,000 milliliters to liter. That drops out the milliliters. So I have the denominator. I'm good with the denominator. I need to kind of continue on the next line here. For the numerator, I need the molar mass of H2O2. Grams per mole, that'll cancel the grams and get moles in the numerator, which is molarity. So that's water plus 16, 18 and 16, 34, around 34. And there we go, this is molarity. You do the same, but with the 3% here and the other density here for the second one. That's it. Pretty common conversion. You will also do this in 2B. Okay, yes? Okay, page 103. 103, this question. Say your question one more time. Okay, this is page 103. For electrons 5 through 10, the 2 P's for 5 through 10, the TAs for this question didn't grade the order of the M sub L. They only graded horizontally if the M sub L matched all the other numbers. So we didn't care the order there. Technically, it would have been the 5 and 6 are -1, the next 2 are 0, the next 2 are +1, but we didn't care. Okay? All right, next. Yes?
If you do your poll 2008, like from final number 24.
Whoa. Okay, fall 2008.
Number 24.
All right, yeah, this is a mixture. This is a Tupac problem. Are you in his class? This is an homage to him. Okay, he likes this kind of stuff. Maybe that's why you don't know it then, because I can imagine him doing this in class. We have a mixture of CH4 and ethylene, C2H4. That's together. Okay. We combust this to form CO2 and water. And we read the hint. Write and balance the chemical equation for each reaction before starting. We gave you points for that year. So you'd actually do that for both reactants. So they want you to write this out and balance it. Is it okay if I just leave the balancing to you? Okay, cool. So then, this here, all of this H2O there, that is the, where is that number? Oh, we don't have that number. We have the CO2. Shoot, I circled the wrong one. CO2 is 14.5. Okay, so the sum from both reactions is that. And then this is the sum of both of these is 5. Okay, and then what's the percent mass, basically? Here's what I would do. Okay, let's say the mass of this one is X and the mass of that one is Y. So I would just say, well, X plus Y equals 5. One equation, 2 unknowns. I need one more equation, right? So what I would do is say, well, X, that's for CH4. X, oh, I need to balance it, shoot. This is 2, that's 1, 2, 3, 4, okay, 2. There we go. So this is CH4, remember? Oh, sorry. Okay, this is CH4, and that's mass. So I need to convert to moles. I think for CH4, 16 grams per mole. And then there's 1 mole of CH4 for every 1 mole of CO2 in products. And then I'm going to convert to grams. You'll see why I'm doing this in just a second. Okay. And this is for CO2 44.01. Okay, now unfortunately I have to bounce this stupid second one now. So this is 2, 2, 4, that's a 2. This is 4, 5, 6, a 3 here I think. Okay, I think that's it. Do this for Y, okay? Remember this is the C2H4. All this garbage again. So the molar mass of C2H4, that adds another 12, I think that's 28. There's 2 moles of CO2 for every 1 mole of CH4. And then this is again 44.01 grams per mole. Okay, now you're wondering why the heck would I go through this mess? Because if I take these 2 quantities and I add them, it is 14.5. You see that? Now I have 2 equations in 20 minutes. Solve. I'll leave the rest to you. Okay. Next. Yep. Whoa, what is this? There's not going to be this crazy stuff. You can ask me later if you're really curious. I'd be happy to solve it, but let me just show. Hey, this craziness, whatever that is. It's too hot. Good job. Okay. 150? 113.
Question 8.
Oh yeah. Okay. This is I have a YouTube video on this that for some weird reason has the most hits of all my videos, and it's so random. Okay. Smallest dipole moment means what about polarity? Polar or non-polar? I'm looking for the one non-polar molecule. Okay? So, that can't be it, is that okay? I'm going to attempt to do this without drawing the Lewis structures. Ideally, you draw Lewis first. That's bent. I drew it earlier. Can't be that one. It can't be that one. It has that weird fluorine on the end of it. So you're down to these 2. I drew the left one in class maybe before, but it's an SO4 unit, and 2 of the 4 oxygens have a hydrogen. So it's asymmetric. It's not this one. If you draw this one, it's fully symmetrical, totally tetrahedral. Is that okay? So that's the best answer. Okay. Yes. No, take it back. Just stretch it or whatever. Can't help asking a question. Okay, that could be true. I think this is my review worksheet. Is that right? O2, that's a 2p4. So this should have 1 more electron right here. But I think the total count is right. 4 and 3 is 7, 2, 4 is 7. This, the middle is right. There should be just 1 more electron. Okay, one more time. This should have 4 electrons here. That's the only. It should have 1 electron right there. Otherwise, it's all good. Cool. That's for my review worksheet. Yes, in the half. Yeah. What? Okay. Do you have a question, or you just want to ask about it? Should I show the picture? The question is, when you sum the partial pressures equal the total pressure? I didn't have to use it, but you can use it on the Dalton's Law problem. Here it is. You could have used it here to not do this formula and just said P total minus this number is that. That's the only place you could have used it in this problem. Okay, right next door, yes.
That's 102, number 26.
Page 102. Number 26, page 102. Oh, this one? This? Also a Tupac problem. He's really popular tonight. All right. This question, again, page 102. Okay. XY. Okay, you mix that. Okay. So those are mixed. Okay. This, you mix again. Okay. This equals that. Okay. So this is a dilution problem, but when there's multiple dilutions going on, it's hard to use the typical dilution formula. You want to go back one step to use the major concept. Moles initial equals moles final. That's what we're going to use. Okay. What is the total volume of this mixture here?
59.
Yeah, 50 plus x. Remember, this is x. So 50 plus x. So what you're going to do, tell me if this works for you. Multiply these two to get moles for the resultant. And then multiply all of these to get moles. Sum these and equal to this. Should I write that? What's that? Oh, okay. Sorry, I want to go fast enough, but not too fast. You know what I mean? So, I want to make sure we get to everybody, but I don't want to confuse you. See how I'm multiplying them all? Is that okay? One unknown is x. Okay, no problem. Yes?
Page 113, number 15.
Wow, 113 sounds like a really bad page. Whole thing, you get stuck on something in particular. Whole thing is...
Yeah, the whole thing, please.
Okay, the hard part about this problem is two parts. Okay, one is stoichiometry, because it's a titration problem. The other is, to do the titration problem, you need a molar ratio. So you need to balance the reaction, but the reaction is a redox problem. So you do a redox and stoichiometry, put them together. That's why it was hard. So I'll write that out a little bit for you to see if it works. Okay. Iron ore. It has iron oxide, which is ferrous. It can be analyzed by dissolving it and turning all the iron into ferrous, which is B+. And then you take that ferrous and you titrate it with potassium permanganate. Okay? It reduces the manganese to Mn2+, and this to ferric. Okay, I'm going to ignore the potassium. I don't see where you went. Oh, there you are. I'm ignoring the potassium. I'm going to erase it right now. Anybody know why I can erase it? It's a spectator ion, chapter 5. Spectator ion. Okay, here's the redox. You have to balance that. I'll skip that if that's okay? Okay. The other part of the problem is to do the titration. So the permanganate, you just write down the numbers. Is this times 10 to the minus 2 It's 41.56 milliliters. So what they want is they want you to change this to moles. Okay? Do a molar ratio, which you don't know until you balance it, to get the moles of this, and then change this to mass. Is that okay if I have you do that?
Oh, yeah.
Okay, good. So then, that mass tells you how much of this there is. And then you're going to go, they want the percent mass of this represents all the iron in the iron ore. They got it all out and changed it to this, which is this. So you're going to take that mass that you found, you're going to divide it by the total mass, which is given in the question, and multiply by 100. Okay? Yes? How do you know? Do you have a specific question? Okay, can somebody, I'll go this way. What number? Number 11, random test. Oh, this is my test. Winter 2011, number 11. Winter 2011, number 11. You want to know which one's ideal, right? Okay. Ideal gas behaves best when you're at low pressures, and high temperatures. So, this is a really high pressure. 760 is like atmospheric pressure. So you want to be closer to 760. Is that okay? So it's not B. Let's see if there's any other high pressure. This is a high pressure also. Atmospheric is 1 atm. So it's not C because of the pressure, both situations. Okay, let's look at the temperatures. All the other pressures look fine. That's a good temperature. That's high. That's a high temperature. This is a little low. It's not too low, but I prefer A and D because they have the higher temperatures. Is that okay? Now, between A and D, I have water and neon. The noble gas is more likely to behave like an ideal gas than any other molecule. So for that reason, because it's neon, I'm going to pick B. So you selected the right answer. Okay, next. Right behind him.
Page 102.
Page 102. After Anthony, I'm going to do one more and then we'll. I got to go watch TV and stuff. Okay. You said page 102?
Yeah, number 27.
Okay, one more question after it. Number 7?
27.
27. Okay, this one right here. This one right here. Okay. Got a balloon. Cleaners. Okay. So I want to know the final volume. Okay? It starts out at this. So the moles change. So I'm using this volume and moles are changing. I want to know this one. I know V1 is 1.20 liters. The problem is I don't know the moles. Okay? To get the moles, I have to look closer at the reaction. So it's NO2 goes to N2O4. Okay, let's say this is X or whatever. All right, and this is 0 initially. It says that 2/3 of X react. So at the end, is that right, 2/3? 2/3. So how much, and this is start, then how much is there of this at the end? 1/3. Yeah, 1/3 of X. Is that okay? 2/3 are gone. All right. Oh, let's also balance this, too. All right. Now here's the crazy part. How much did I make of this? What's this? Yeah, because of the molar ratio, I make 1/3 of X. Why is that true? Well, I start with X moles of NO2, and then I have 1 mole of N2O4 for every 2 moles. 2/3 and 2/3 react. So let's start here. 2 moles of N2O4, but not X reacts. Only 2/3 of the X react. Is that okay? So it's not just X. It's X times 2/3. Is that right? The other 1/3 doesn't do anything. This turns out to be 1/3 X. So that's how I get the number in the box. Okay, here's the crazy part. N initial is what? According to this. X. I start with X in the start. There's 0 here, so just X. What's the final? 2/3 X, because there's 1/3 of this and 1/3 of this. Is that okay? Okay. So X will cancel out. I'll let you solve it through there. Last question. Saw you first. Yeah.
Page 108, problem 19.
Page 108, number 19. This one right here?
Yeah.
Okay. So also a pretty common question. So it's good to be able to do this one. We have second orbit. I want to know the wavelength, right? If we're talking about orbits, it's the Rydberg equation.
Yeah.
In my class?
Yeah.
Okay. So an initial square.
There's a glare.
Is that better?
Yeah.
Okay. And final. Oh, that looks really ugly, but hopefully you kind of get it. Okay. So, and this equals HC over lambda. All right, let's get a different color pen. Initial orbit is, anyone? 2. It starts there. What's the final orbit? Infinity. It's gone. 1 over infinity. That's what happens whenever you ionize something. So you just drop the second term. Okay? So H is a constant, RH is a constant, and C is a constant. So can I have you solve from there?
Yeah.
All right, cool. Good luck.